I'm very excited to introduce you to a whole new neural network architecture called the autoencoders. Before I do that, let's take a step back and look at what you learned in the collab. One of the things that we introduced to you was k-means, which is a machine learning algorithm that's specifically based on clustering, and that allows you to segment data into different clusters as centroids. Now, hopefully by doing machine learning using k-means, we learned that one of the key problems that k-means has is that as the data set increases, or as the number of observations that you have in your collection actually increases, k-means starts to fall apart. Especially when you have high dimensional data, it does really poorly. So that leaves us with this fundamental question about what do we do with anomaly detection? Remember, with anomaly detection, the problem is that we have a lot of data for the normal behavior, and it's really the important and rare events are the ones that we care about the most. So how do we go about solving that problem? Well, let's take a step back and look at it more intuitively. Well, we have, to come to terms with the fact that we don't know what we don't know. What do I mean by that? Well, you and I don't know the thousands of ways in which the machine might fail. But there is one thing that we know really well. We know how the machine is supposed to work. And so you do know what you know. In other words, if I take you back to this data and show you the wealth of data that we have here when the machine is working normally, well, then you know how the machine is supposed to work normally, and you say, yeah, that's how it's supposed to work. And you don't know the various anomalies that you might see down the line, right, through the life cycle or the lifetime of the machine. And so when everything is good, you know what the pattern is supposed to be. Can we exploit that? That's the key question over here. And the answer is yes. We can exploit the fact that we have a lot of normal data, forgetting about the anomaly itself. How are we going to do that? Well, what we're going to do is effectively, we want to build in an ideal class, a neural network that can act as an identity function. In other words, it's supposed to be able to take an input and regenerate the exact same input. And so can we train the neural network to do that? The answer is absolutely yes. Because we have lots of normal data, we can certainly architect a neural network to be able to take a set of inputs on the left-hand side and spit them out on the right-hand side. And the key question is, what is the architecture in the middle? What does it really look like? What does it need to be like? Well, that's where the interesting aspects come in. When you have a lot of input signals that are coming in, there's a lot of noise in these signals. And what you really want to do is you want to compress that input signal down to its core fundamental elements, its basis functions, in other words. You want to be able to eliminate the noise that's in the signal and really get to the essence of that signal. And that's where the autoencoder part comes in to bear. The autoencoder idea is like this, that you want to create an encoder network on the left-hand side, and the job is to take this high-dimensional data that's coming in the input neurons and to compress them down into its core compressed latent space representation, which we can then deconstruct by the decoder and then reconstruct the original signal on the right-hand side. Effectively, this would mean that we have a set of neurons that are on the left-hand side for the encoder and a set of neurons on the right-hand side for the decoder with this sort of architecture. And what we are compressing, the information down on the encoder side by pushing it through fewer and fewer neurons so that the network effectively learns to figure out the hidden core. And then from that hidden core, you can train the decoder side of the network to learn how to correctly reconstruct the original image. Now, because we have a wealth of normal data, we can certainly do the backpropagation process and repeatedly train this network through all the traditional mechanisms that we have learned so far. And in doing so, because you have so much of the normal data, it's possible to get a reconstructed network that minimizes this delta or this error between the input, what the input signal looks like, and what the output signal needs to look like. And in fact, you want to minimize the reconstruction loss. To be more specific, let's say I give you this example over here. And I want this network to be trained repeatedly until it's able to reproduce this output on the right-hand side. At every single stage, I'm going to take the input from the left and I'm going to take the output from the right, and I'm going to compare them and do a diff and see what's the mean squared error, what's the reconstruction loss between these two. And I'm going to push the network repeatedly through this training process till it minimizes that mean squared error. At that point, my network has learned for a given set of input how to reconstruct the input when it sees that same signal. And that's great because this means that I have a really good low reconstruction cost or reconstruction error. And that's the critical thing. Now that your network has actually learned how to reconstruct your wealth of normal data, when you throw it some abnormal data, like something that comes from, say, MNIST fashion data set instead of the numerical data set, now suddenly when you ask it to reconstruct, it's going to reconstruct something like this. And it does not look anything similar to what the original left-hand image looks like. At this point, if you were to compare the two pixel by pixel, what you would end up finding is that the left-hand image does not match the right-hand image, and therefore you have a very high error. And that is the key nugget of anomaly detection, because voila, suddenly you have trained this network to raise a flag and say, hey, here's an error that I have, and I have a high error on this because I'm not able to reconstruct it. And that's a beautiful thing. So unlike traditional supervised based learning methods where you typically want the error to be as small as possible, here it's almost like you want the network to try and generate that image, and it's not going to be able to generate the original image. And when you do the diff between the two of them, the error is going to be significantly larger because it only knows how to reconstruct the normal data that it's trained on. And when it sees abnormal data, the error is going to be a large, in its reconstruction. So that is the key for doing anomaly detection using autoencoders. Now, I'm super excited you learned about autoencoders because they are a very powerful piece of technology that everybody is quite excited about. And it's got many applications because anomaly detection has a very fundamental structure and can be used in so many creative ways to find all kinds of anomalies, and can be used as a signal for predictive maintenance and for conditioning monitoring. One thing that you're going to be going through in your collabs is learning how to tune the anomaly detector. So you have a deeper understanding of how to calibrate the thresholds before you flag something that's anomalous or not. And there are a couple of other things that you're going to pick up in this class, and I'll see you back when I'm ready to wrap up part 2.